Welcome once again to this course on convex optimization. We had been discussing for the last few lectures on linear programming problems. Now, one might know that in this group of NPTEL courses that you can see over the internet or through the YouTube, there is a course on linear programming, largely based on combinatorial approaches stemming out from the simplex method. Then the question will be why I need to discuss linear programming here separately. Let us understand that this course on convex optimization is about the theory of convex optimization as well as the solution methodologies, and trying to really tell you about the most important class of convex optimization problems. It is important to know at the very outset that a linear function is a convex function, which I am sure you understand by now. Here I have two pictures. So, every linear programming problem is a special class of convex programming problems. Now, the question is, how practical is the simplex method that we have just learned? Now, the simplex method that we have just learned, one has to remember that it is not the run of the mill approach that textbooks take with Tableau. I cannot say run of the mill, but the standard sort of approach one should say that the textbooks take. But here what we did was an approach due to Manfred Padberg, which does not use the Tableau, but just does updating based on very simple ideas, and that is exactly what the simplex method does and exactly what linear programming solving algorithms would program at their back. The solving softwares have programs which is based on such an approach. Computers are not calculating tableaus, that is something we have to remember. So, the approach of linear programming done here is different from the course that you will see, possibly they are already on the internet, and here we are now entering into one of the most exciting methodologies for linear programming problem, which can be also extended to convex programming problem. We will see such an extension for semi-definite programming problem just after a few lectures, once we study a bit about interior point methods for linear programming problems. Now, interior point methods is slightly different from the simplex method that you have studied. Just to give you a little idea, if you have a convex polyhedron like this, so if this is your C, what the simplex method does is to move from one vertex to the next, not just moving from one vertex to the next arbitrarily, but doing it in such a way so that at the new vertex the objective function value either remains same or it goes down. In the interior point methods, we start from a point in the interior of the feasible set, that is all the components of x are strictly bigger than 0, and then we move along certain path described by certain equations towards the solution. So, we move in the interior. So, that is why it is called the interior point method. Now, the question we ask here, you see it is written, how practical is the simplex method? Now, one can say that okay, come on, simplex method is very practical. There is a huge amount of industrial problems which have been solved by simplex method, real mathematics by the way. But here we are meaning not practicality from the practical point, from the point of view of practicality in the sense of applications, but we are talking about practicality in the sense that from an algorithmic point of view, is it practical, that is whether it is polynomial time, that is whether you know that, or whether you are guaranteed that in a certain steps which you are going to finish running this algorithm, that is the number of steps required to reach your desired solution, your level of accuracy is bounded by some polynomial, that is it cannot be arbitrarily large. Victor, Klee and Minty in 1967 showed that if there are certain linear programming problems which can become really very bad. So, the time complexity, in the sense that the number of iterations required to solve such problems, they showed, can be exponentially large, and that is not what is practical from the point of view of running algorithms. Now, the interesting part is that the interior point approaches guarantee you a polynomial time algorithm for linear programming. Now, but what are interior point approaches? The interior point approaches, apart from the writings that you see there, the interior point approaches is to use a nonlinear programming approach to linear programming. So, what does it mean by this? The first revolution in this area was in 1984. Linear programming, almost people thought that it was just simplex method and its variations, and that is enough, and you can say bye bye, there is nothing much to do about linear programming, but to have it built in softwares and apply them. But in 1984 there was a revolution which revitalized linear programming and also brought back convex optimization to the center of all the action in optimization theory and applications, because people were so obsessed at that time in the 80s about non-convexity that they hardly bothered about convexity. Convexity was taken to be something very classical, more applications are in non-convexity, and so we should bother about non-convex case, not the convex case, but this revolution brought every convexity back to the center stage, and this was a famous algorithm called Karmarkar's algorithm due to a mathematician called Narendra Karmarkar, who now stays in Pune, and we should be proud that he is an Indian, and he, when he was in Bell Labs, he had he did this interesting algorithm. But of course, I would not take my time to, but there is a lot of, keeping in view the limited number of lectures I have on this subject, that I cannot really spend time on Karmarkar's algorithm, because it is too detailed, needs a lot of detailing, needs a lot of ideas, because it needs a lot of geometric concepts are involved here, especially from projective geometry, notions of projective mappings, etc., which might deter the viewer, especially who are not so mathematically inclined. So, we will go and take a different approach. After 1984, what happened, Karmarkar made a comment which could be, which may or may not be too much of overstating. He said that in many cases his approach, his Karmarkar's algorithm is much faster than simplex method. So, this thing sparked a revolution, and this thing led to many more researches in the area of nonlinear programming, many more developing the ideas of Karmarkar, many more really looking at very different approaches. The approach that we are going to deal here in this particular lecture comes out of a very simple fact, a fact which we have already studied. We know that the Karush-Kuntakar conditions for convex optimization problems is not only necessary, but also sufficient. So, if you know that there is a feasible x and there is a Lagrange multiplier lambda which gives you a KKT point, then x is an optimal to CP. And the interesting fact that once you write down the linear programming problems KKT condition and try to solve those KKT conditions, you are getting a interior point method which is polynomial time, and that is the strength and the beauty of this approach, because this approach can be understood by most people, because it is simply equation solving. Now, we go back and write down the linear programming problem LP and its dual. Now, I just want you to remind that given this linear programming problem in the standard form, this is the dual which we had already calculated when we were studying the Lagrangian duality results. So, the Lagrangian dual of this problem is this. Now, you might have forgotten it by now, but YouTube is, of course, you can go back, something in which you can go back and have a look, but now just to recall you as to how to build this dual, instead of going to Lagrangian duality, I would like to rather show you a simple approach just directly taken off from the primal problem, to show that there is some problem going on at the back of it. So, how to construct the dual? Now, you have a x equal to b. It does not matter if I multiply with a element, multiply means taking inner product. So, this is always true for every y. So, this implies I can write now what I want is that if I want to find a lower bound to this problem, the primal problem, how can I find it? If I know that there is a lower bound, there is a famous theorem and which we have also proved it here, that it will show us that this has a solution. So, now observe a very simple thing. The simple thing is this, that let me consider C minus A transpose y to be an element of Rm plus. That is, all the components of this vector is greater than equal to 0. That is, choose y element of Rm in such a way that such that C minus A transpose y is in Rm plus, that is C is bigger than equal to A transpose y. Now, if you observe, C minus A transpose y is in Rm plus, and because x is a feasible point. So, since x is greater than 0, since x is feasible, we have C minus A transpose y, because all the components are non-negative, inner product with another vector whose all components are non-negative will give me greater than equal to 0. And this would immediately show me that C of x is bigger than equal to A transpose y x, which is bigger than equal to b y. So, if I can fix up some y like this, then for this given feasible x, for whatever feasible x I choose, I will be through, I will be getting a lower bound. So, for all x in Rn plus, this is true. So, for all feasible x, whenever x equal to b and x is greater than equal to 0, if I can find a y such that C minus A transpose y is having components all greater than equal to 0, then B transpose y or B inner product y is giving me a lower bound of the original linear programming problem. So, that is something fascinating. So, which means that this is true for every such y which satisfies this. In fact, if I maximize this now, that will also, as the maximum will also, or the supremum will also act as a lower bound. So, in effect, to find the lower bound, we shall solve the problem maximize subject to A transpose y less than equal to C. But of course, I can add a slack variable to make an inequality into equality, and this would lead to max of, which is exactly the one I had written earlier as a dual. Now, we will call this problem as DPE, which means we have got a slack variable here, or maybe just change this name a bit, DP equivalent, right, and the original DP which comes out naturally is this one, DP. So, dP, and by adding the slack I get a dPe. Now, this will give me, now once I write down these things I need to put down some notations which would be useful as I study interior point methods. The feasible set Fp, instead of writing C, now we will start writing the feasible set as Fp, because that is why, because this is the standard notations that you will get when you look at the literature in interior point methods. So, that if anybody here is interested to go more into optimization and really look up the literature, then this is the symbol he will get when he studies interior point methods. So, this is now, of course, for the dual problem, the feasible set, the primal feasible set you can call this, sorry, dual problem you have y element of Rn, Rm, such that A transpose y is less than C. Now, when we write the dual problem in the equivalent form, that is if I want to write something like this FDE, you must observe that the dual feasible set is in a higher plane, in the sense that it is in a higher dimensional space, because now it will have y and s. So, it is Rm cross Rn with A transpose y plus s equal to C, and s is greater than equal to 0. Apart from these two sets, we would also require its interiority, that is, we will require the what we will call the strict set of strict feasible points. We will have to put some sort of interiority conditions. So, this is called the dual feasible, dual equivalent, dually feasible we can say. We are just inventing some symbols, but okay, that is what it is. One must remember, when you add a slack to a dual problem, though the problem at the end remains equivalent in the sense that you have the same solution, but the feasible set is no longer equivalent in the sense that they are in two different spaces. You cannot say this coincides with this. So, any y which will satisfy this, there would be a s for which y s would be in this. For any y s which satisfies this, that particular y will satisfy this. So, equivalence in this sense, but not in the sense of exact matching of the sets, exact equality of the sets. So, we will talk about strict feasible point. These are some things. Strict feasible point will basically you have been pushed into the interior of the feasible set. Now, the same thing. So, I will for the primal one would have x in Rn. Now, x would be here strictly bigger than 0, means in the interior of Rm plus, that is every component of the vector x would be strictly bigger than 0. Remember, again it is not greater than or equal to 0, but every component of the vector x has to be strictly greater than 0. This subtle difference is very, very important and will play a very fundamental role as we go along. And then it remains the same. You do for the dual, just remember, wherever there is an inequality of greater than or less than equal to type, you convert it with a strict inequality. The inequality is replaced with its stricter version. So, this is for the equivalent problem. Of course, there are some authors who analyze the whole thing in a more combined form, that is they will choose the primal dual solution set. So, here instead of how to differentiate with this, you might say okay, you have taken the same symbols. So, in order to differentiate, we will just put a round circle on the top, and that is exactly what has been done in the literature. So, some authors would prefer to have a combined primal dual feasible set, that is they would like to write this as and of course, there is a stricter counterpart. So, we would continue to use any of the formalisms, but we will largely focus on this sort of formalisms. What is the relation between the primal and the dual? That is the question. What is the relation between LP and DP? Now, you know that if Slater's condition holds in the primal problem, and if the primal also has a non-empty feasible set and primal has a solution, then the dual also has a solution, should have a solution, something like this. What you know about convex programming problem, that if the Slater condition holds and the primal has a solution, then the dual also has a solution, and the solution values are same, their optimal values match. But the interesting part of linear programming is that you do not require constant qualification. Linearity itself is a qualification condition. So, what we did in the case of convex programming problem was to use the Slater condition and make a proof of what we call strong duality result, which is the equality between the maximum of the dual and with the minimum of the primal. But for the linear programming problem, we do not need any conditions, and for that we need a different sort of proof, which depends on alternative theorem called Farkas lemma, which we will also state, but we will not do the proof now. But what we will write down is the fundamental duality theorem for linear programming. We will write down the results and look at its consequences, but we will not go into the proof at this moment. We will do it tomorrow. If we feel that tomorrow is also it will get too much complicated, we will do it maybe after 1 or 2 days when you get more or less habituated with this stuff, fundamental duality theorem. So, let me write down the fundamental results about duality. So, the 4 cases can arise. Number A, so we will write them down as A, B, C, D. So, number A, both problem have solutions x star and y star, that is they are they are feasible, and then the optimal values are same. That is, so x star is the primal solution, y star is the dual solution. I understand that you know by now that x star is the primal variable and y star is the dual variable. This is obvious and I do not want to make a special remark about it. So, this is equal to the minimum value of the primal equals to the maximum value of the dual. So, this is some authors would like to refer to as normal case. So, the results that I am writing down here are from a book by Wilhelm Forst and Dieter Hoffmann called Optimization Theory and Practice. This is a very good book for anybody who intends to do a graduate work in optimization. A lot of things to learn from this book, and this book can be used even by expert optimizers. The second thing is that the primal has no feasible point. And the dual has a feasible point. And the dual optimal value is plus infinity. The dual has no feasible solution, but the primal has a feasible solution. And then the primal objective value is minus infinity. Cannot say it is minus infinity, this is a vague statement actually. Other primal optimal value is minus infinity, we cannot say that, but we say that these are unbounded basically. Primal problem is unbounded below, dual problem is unbounded above. So, which is a shortcut way of telling this is dual optimal value is this, primal optimal value is this. And the last one is both of them are feasible. So, if both of them are feasible, what is happening? If one is feasible, other is not, what is happening? And the third last is both of them are not feasible. So, neither are feasible. So, these exactly one of the above four holds. Now, we have to say okay, this is what we know about the link between the primal and the dual. This will be very fundamental, this will give us some idea when we write down, we study a bit more. Now, the question would be, how do I devise my optimality conditions? What is the optimality conditions for the linear programming problem? Or the KKT conditions for the linear programming problem. Okay. If you go back at the saddle point theorems, I would just like to recollect the saddle point results. Give me a shot. You see the saddle point results here, Gix is less than equal to 0. If in for the standard LP problem I have Ax equal to b, my x less than greater than equal to 0 can be posed as minus x less than equal to 0, and Fx is nothing but C transpose x, and Slater condition in that case automatically holds, and since A is taken to be full rank, then we can automatically get the optimality conditions following this thing. So, let us go back and you see here, see linear programming in the standard form we have written it in this way, and in this case also we have written down the dual, and what we are now going to say that we can use the saddle point results that we have here, the saddle point conditions, to write down about the duality in linear the optimality in linear programming problems. Now, so now my condition is, my problem is minimize Ax equal to b and each xi is equal to 0, each of them consisting of, this is g1 x1 x2 xn equal to xi greater than equal to 0. So, minus xi is the g, right. So, if I can write this equivalently as cut kitna time. So, here I is from 1 to n. So, you can see Slater condition actually holds, and I have taken this to be full rank. So, all these are linearly independent, and so once I know this fact, so I can construct the Lagrangian. In this case, let us go back and see what sort of Lagrangian we had constructed. See, this is the sort of Lagrangian we had constructed. Okay, this would be the minus xi's are taking this place, and this is the way we have constructed the Lagrangians. Okay, and this is what we had. So, we go back, we come here to our study. So, we would keep some instead of lambda I am putting s here, because the Lagrangian multiplier associated with this is nothing but the dual slack. So, let me just write it down. Cx plus y into b minus ax plus minus S1 into x1 minus Sn into xn. This is exactly, or S1 into minus x1, maybe that is a better one. I think that is a better way to write S1 into minus x1, the way we had written earlier. Now, what does the Karush-Kuntakar condition say? I have not yet done Karush-Kuntakar conditions for this very this case, because this would need some more results. So, let us go by some sort of intuition, some sort of gut feeling, I guess. Sometimes in math you have to use your gut feelings, it is not that every time. Why I do not want it to go into the proof of this, because the proof of this would require some sort of theorem of the algorithm, which is called the Mochkin's theorem of the alternative, or you have to make some complicated application of separation theorem. So, I do not want to deter you from the course, but because I would just keep on doing some proofs, but the idea is to make the main ideas through, rather than getting you bogged down too much in the proofs. I would give you the proof of the strong duality theorem just as an example how proofs are done in optimization, and the use of certain very important results called Farkas lemma, which are nothing but very special applications of separation theorem. But okay, going by what we had in case of the Lagrangian multiplier rule, what we would have is this. Should be 0. Number 2, we should be having x to be satisfying this. We should also be having, because of feasibility, and fourth we will have, this is the complementary slackness condition for the inequality constant. So, S1 into minus x1 is 0, plus S2 into minus x2 is 0, plus Sn into minus xn is 0, each of them is 0 individually. So, if you sum up, we will get this is equal to 0. Now, once I know that this is what the KKT conditions are, this is what are my KKT conditions. I have not yet proved them, but I am just writing just down from gut feeling. You should know that the Lagrangian, whatever be the Lagrangian, when you differentiate it with respect to x, it should be giving you 0. That is the solution x, given the solution x, there exists y and s such that x, y, s, x forms a critical point of the Lagrangian function value, Lagrangian function when y and s are given. So, here what we will do now is that we will write down this slide this explicitly. This will just give me, if you look at the whole thing, it will give me, because it is in terms of x. So, it will give me and then this is as it is. I can just change it a bit. KKT condition for LP. But what is this KKT condition? What have we done? What we have first written the dual feasibility, then we have written the primal feasibility. The dual feasibility first line, primal feasibility, and just we have this additional condition called the complementary slackness condition. Now, the very important thing is that this is the crux of everything, the complementary slackness condition. This is the link between the primal and the dual. Now, just if you look at it, this is a system of equation. So, I can just put the S on the other side, I will make it slightly more good looking and I will put it like this. Sorry, it was C minus, the first part was C minus A transpose y equal to S. The first I made a mistake, it was C minus, here was a minus, A transpose y was equal to S. So, now I am making it slightly good looking by putting it as A transpose y plus S minus C is equal to 0, Ax minus B is equal to 0 and x transpose S is equal to 0. So, you see this 3 forms a system of equation, and these 3, because it forms a system of equations, I can solve them by certain methods. The method is the Newton method that we will employ, but while we solve them we have to keep an additional eye, an additional watch, that x for every solution x has to be this and s has to be this, that is x has to be greater than or equal to 0, s has to be greater than or equal to 0. If I have not done this, then if I do not check this, then I am actually not solving the KKT conditions, I am just solving this system. So, to solve the KKT condition, I have to solve this system as well as these 2 inequalities. So, how do we do that? To do that, we have to do Newton's method. So, instead of getting into the details of Newton's method today, because it will take quite a bit of time to explain to you what Newton's method is, I will rather concentrate on speaking about Newton's method tomorrow, but today I would just like you to have a look at it and rather think of how does one solve this problem and how does one get this KKT condition. Is there any way you can do it? I would like you to have a thought about this problem. Is there some other way you can thought of proving this? Is there some way out? So, if there is some way out, it would be good to figure it out, or at least try to see whether from here to here it is making sense, and try to see whether you can have you really understood how the dual is constructed, right. So, these are the very basic things that you will require. You also have to get used to this this kind of sets that we are using. So, all these things are required. So, we will go to the Newton's method tomorrow, and so tomorrow the first job is to see how to apply the Newton's method to solve this. Once we know this, then we will go into the proper issues of the interior point results. And okay, before I leave, I give you homework. Let x be feasible. So, I am giving a solution. Let x be feasible to the primal and ys is feasible to the dual equivalent, and C transpose x is equal to B transpose y, then x solves LP and y solves DP. Prove this. This will be your homework for at least this evening as we wind it up today. Thank you very much. See you tomorrow and start from Newton's method.